So today we're going to start a unit that's usually just called logic. This is a unit that you do that regular geometry does not do. It's one of the differences. So today we're just going to talk about an introduction to logic, which is called inductive reasoning. Inductive reasoning is being able to see patterns in things and figure out, well, what will come next in the pattern. Okay? Frequently, intelligence tests use the ability to, look for patterns and find what's coming next as a way of judging how smart you are. Okay? So, let's look for the next item in each of these patterns. So, if I list the following three: January, March, and May, what do you think might come next?
July.
July? Okay.
R. There's no R in July.
Thanks for the tip.
Yep.
All right, how about this number pattern? 7, 14, 21, 28,
35.
35. And then this pattern of triangles. So this one kind of points up, and that one points to the left, and this one points down.
Right. That one.
Okay, so pointing to the right might be what's next. So my question to you is, how confident are you of these answers?
Very
Of these
confident.
ones in particular?
Yeah.
Good.
What if I told you they were all wrong?
Dang,
That
that
was
sucks.
then you're wrong.
I'd be very
Well, what if I told you that, the first ones were people's months that people in my family were born, and none of us were born in July?
I'd say you didn't give us enough context, please.
Okay. And what if I told you the second one was the number of points that the football team that I follow scored on consecutive Sundays?
Man, that first game was bad.
And then the next week they only scored 10 points.
They suck.
And what if I told you on the last one I just randomly spun it around and that's not the way that it went the next time?
I would quit the class.
So from what you're given, these are probably the best answers, right? But are we for certain that they're the right answers?
No.
No. Based on what we know, this is our best guess. That's inductive reasoning, where you take what you know, you take the pattern, and you go, well, I think that this is what would happen next. How confident of it are you? Well, depends. Yes?
We did it in biology, and it ended. The wolf gave the rabbit a piggyback ride because she got tired from dancing.
That is inference and observation. Nothing like
Interesting.
Oh,
I'd like to know more about that, but not right now. So, making a conclusion based on a pattern found using multiple examples is called inductive reasoning. A statement that you believe to be true based on inductive reasoning is called a conjecture. Okay? When you make a conjecture, you're saying, this is what I have observed. This is the pattern that I see. Okay? And again, I will caution you, when you use inductive reasoning, sometimes you end up with the completely wrong answer. Okay? Let's say, for example, let's just make up something ridiculous, that every time your Aunt Martha visited, your dad caught a cold. And it happened 3 times, and you're like, oh, Dad's allergic to Aunt Martha. Is that possible?
Yes.
Yeah. Is that for certain?
No.
No, he may be faking it. He just doesn't want to be anywhere near her. Okay? We don't know. Okay? So when you base something, and that's a silly example, but there are serious ones too, where people start judging groups of people based on very limited experience. Okay? Pardon?
That's not good.
No. And then you start putting everyone in that class. Let's say that you were picked on by tall people
Is she short? Who's she?
for whatever reason. Okay? And then you started to distrust tall people because there were 3 tall people that picked on you at one point. Right? You're overgeneralizing. And that can happen. Okay? But on the other side, inductive reasoning is super important because it's how you learn almost everything when you're very young, especially. You learn not to touch the hot stove. Hopefully, it doesn't take 3 or 4 trials before you go, yeah, I think I'm going to stop touching that. Okay?
But what if it didn't hurt, like just that once? If you're going to do it again until it does hurt, you learn not to. Wait, what if it
Yes.
doesn't?
If we have time later, I will show you a cartoon about that. All right. So let's complete these conjectures. And these are more ones where it's like they're numerical laws. So we're way more certain of this. So the product of what does product mean, by the way?
The plus.
When you multiply them.
Multiply of an even number and an odd number is
Odd.
odd. So if you just pick an even number, 4 times an odd number, 7, what do you get? 28. Is that really odd?
Is 1 an odd number?
Oh.
Would that
This
only
should-
work if you're adding?
If you add an even number and an odd number, yes, you will get an odd.
I'm so smart.
What happens if you take the sum of 2 evens?
They're even.
It's even. And what if you take the sum of 2 odds?
Even.
It's even. God bless you.
It doesn't seem fair to the odds.
Because they're odd.
Like you.
So, if a positive number is divided by a number between 0 and 1,
Does between mean it could be smaller or 1, or just everything from like 0.0 to like 0.9?
it means in between.
So it can't be 0 or 1. Okay, cool.
So, so pick a positive number.
1.
6.
Okay.
Oh my God.
And let's divide that by a number between 0 and 1.
0.5.
Okay. What is 1 divided by 0.5? And please do not tell me it's 0.5.
It is
Two.
2.
It's 2. Thank you. Don't believe me? Whip out a calculator and do it. 1 divided by 0.5?
Why would we do that? Why wouldn't we just believe you?
I believe in healthy skepticism. Do you just believe things that people say? Frequently, you look at me like that doesn't make any sense. You're very skeptical.
I gotta agree with your answers.
All right, so let's do another one. Let's do 6 divided by
0.1.
0.1.
60.
That's 60.
That's a big number.
So if a positive number is divided by a number between 0 and 1, the result is, well, yeah, greater than the original number.
If we put bigger, would that be wrong?
No, but let's learn to use the correct words. Because, I mean, if you want to be silly about it, That number's bigger than the 40. The 8 is bigger than the 45.
I was very confused for a second. I was like, but it's small.
Exactly.
0.1 goes into 60.
Goes into? All right. Let's try this one. Here we're trying to find a pattern. So, what do you notice the n is going up by each time?
1.
All right, it's increasing by 1 every single time. What is the p increasing by each time?
10.
10. So basically what I want to know is, well, what happens when this is just some number n? How can I find this number? Well, we know that this is going up at a ratio of 10 to 1, right? That's slope. So it's going to be 10 times n, but that's not all. Because if it was 10 times n, 3 times 10 would only be 30, 4 times 10 would only be 40,
Plus 20.
Plus your starting point.
That's your.
plus another 20. This is a linear pattern. Then you're not going to like the next one, because it's very much not a linear pattern for this next one. So the number of lines formed by n points. N just stands for the number of points. No 3 of which are collinear. Okay, so how many points do you need to form a line?
2.
Got to have 2. So we're going to make our chart. We're going to go, okay, n, and we're going to say, I'm going to use a cursive L for lines. So if I have 2 points, how many lines do I have?
1.
1. What if I have 3 points? And
2. 0.
so if I do 3 points,
Wait, I'm confused.
how many different lines?
3.
We'd have 3. 1, 2, 3. What about for 4?
6.
Yep, it is 6. It gets harder. What about 5?
25? I'm just guessing.
You're just guessing?
Yeah.
10.
It is 10.
Oh, I was just thinking.
I was close enough.
Did it.
Okay, let's do one more to kind of establish the pattern here. What do you think 6 might be?
16.
Nope,
Is it more?
it's not a bad guess, but it is wrong.
That's a lot. I don't want to draw anything.
15.
It's 15. All right. Is this a linear pattern?
No.
No, although the ends are going up by 1 each time, L is not going up by the same amount each time. Clearly not a linear pattern. Yes, ma'am.
Does that mean the only way you can calculate it is by actually drawing it out? Like, figure it out? Or,
We're going to find a formula.
okay.
Okay? So notice from 1 to 3 is a difference of how much?
2.
And from 3 to 6,
3.
difference of 3.
It's a
Oh, that's
Well,
what is that the second
exponential expo.
No, it's not exponential, but
Quadratic?
not a bad guess. So how many do you think we would have if we had 7? We'd have 21. We would have to add 6. And that's fine. We could find the next one. But what if we wanted to find, well, what if we had, 100 points? You don't want to have to go through all of the ones in between in order to find what it is for 100 points, right? So we'd like to find some sort of a pattern. Now, notice, what's the difference between all of these?
What?
1.
We get a third.
Wait, isn't that quadratic?
Yes, this is going to be a quadratic pattern.
That section in algebra made my brain die.
Well, we'll see if we can make more sense
That
now.
explains it.
So this is going to be a quadratic pattern. All right. Yeah. So with a quadratic pattern is 2 linear patterns multiplied together. Okay, a quadratic pattern is 2 linear patterns multiplied together. So if we look at this one, and this one is one of the harder ones, and this is why I'm doing this one, because it's kind of nasty. It's a quadratic pattern, which means it's 2 linear patterns multiplied together. So I start looking at what sort of patterns do I have with things multiplied together. So for 1, what's the only way I can get 1 by multiplying 2 things together? 1 and 1, right? The only whole numbers, at least. And with 3, what do I have to do? 1 times what? 1 times 3, yeah.
Are we just gonna keep on going 1 times the number?
Well, but that wouldn't be very helpful, would it?
No.
Okay? So, now with 6, I could do 1 times 6, or I could do what? 2 times 3. But this is still not helpful. 1 times 1, 1 times 3, 1 times 6. It's like, okay, that's totally non-helpful to me. Okay? And that's why this one is harder. So sometimes you have to look at it and go, well, that didn't work very well. I'm actually going to make a new chart. And I'm still going to have n on the top. And I won't do any that are harder than this. So I'm going to have 2, 3, 4, 5, 6. And on bottom, I'm going to do 2 times L. This is one of these tricky things that you can do. Sometimes you'd have to use 3, 4. I'm not going to make you do any big numbers. 2 would be the biggest I would ever do to you.
Thank you. Can I go get that?
You want to miss this?
Not really.
We're pretty close to being done. Can you hang on?
Yeah.
Okay. So 2 times L, this is going to be 2. This will be 6, 12, 20, and 30. Now let's see if we can find a pattern of things multiplied together. So to get 2, what do I have to multiply together?
2
Pardon?
2
2
and 1.
and 1, all right. What about for 6? I could do 6 and 1, but that's not helpful.
2 times 3.
Yeah, I could do 3 and 2, right? Okay. And then
Oh, and then 4
for
and 3.
12, I could do 4 and 3.
5 and 4.
Oh, and I could do 5 and 4. And 6 and 5. I like that pattern. Okay. In every one of these, the first number, so 2L is going to be equal to, the first number is just whatever I had in the n column, right? And then the second number
It's -1.
is 1 less than what I had in the n column. So I'll call that n minus 1. Well, I wanted a pattern for L, so L is going to be, I'm going to divide both sides by 2. It's going to be 1/2 of n times n minus 1. Let's see if this works. We said that 7 was going to be 21, right? Let's see if it works. So for n is equal to 7, L would be 1/2 times 7 times 7 minus 1 is 6. That'd be half of 42, which is 21. It does work. Okay? That's as ugly as they get. All right. So I didn't want you to miss the end of that. If you need to run, yes. So conjectures are not guaranteed to be true. Sometimes they don't work out. They may be based on too few examples, or on bad data, or there may be hidden behavior that you don't know about. To show that a conjecture is true, you must prove it based on previously accepted information. That's hard. To show that it's false is really easy. You just need to find one example where the statement is not true. Okay? So, if, for example, going back to something we talked about earlier, let's say that, when I was a kid, tall people picked on me. And so I decided tall people are mean. Pardon? I'm average-ish.
How tall are you?
I'm 5'10" and 3/8. If I was only 1/8 higher, I could be 5'10 and a half, and I could claim 5'11 because I could round up. But no. Okay, so back to the tall people. To disprove what I believe about tall people, that tall people are mean, what do I have to do? I just need to find one that's not mean. They don't even have to be nice. They just have to be not mean. Right? Is that relatively easy?
Yeah.
Yeah. So showing that something is false is always simpler than showing something is true. There's a higher standard for true. For true, it's got to be true all the time. For false, all you have to do is show one time that it doesn't work and it's false. That's called a counterexample.
How would you determine the height of the tall?
Yeah, part of the problem with that is that tall is subjective.
What is called tall?
Yeah. So, it could have been just people who were taller than I was.
But then you grow.
Yeah, okay.
Wow, Jackson, people grow. That's crazy.
Some people don't, but
You don't. I'm saying 5'8" for the rest of you.
I'm not 5'8". I look 5'8".
Oh yeah, 5'4", my bad.
anyway, so let's find a counterexample for each of the following. Number 1, for any positive number n, 1 over n is less than n. All right, so pick a positive number. 4, okay. So if n equals 4, is 1 over 4 less than or equal to 4?
Yes.
Yes. Is this a counterexample? No. This is an example. You have showed how sometimes it works. I want a counterexample. So I want a number that makes this not true. I have to think of a positive number.
1.
1 over 1
It's 1.
is still
Less than or equal to.
4.
Okay, what if m was equal to 0.5? 1 over 0.5, is that less than or equal to 0.5? No, because that's 2, which is greater than 0.5. This is, so n equals 0.5 is a counterexample.
Would that be true if it said any positive number, like 1 and above?
If you said any positive number greater than 1, then this becomes true. You're exactly right. So a lot of times what you have to do to make something true is limit it a little bit to weed out all those false cases. Okay? All right, last one. Supplementary angles are always a linear pair. Is that true?
Yeah.
If you have two supplementary angles, do they have to be a linear pair?
No.
Yes, because it's on a 180 degree.
Okay, what is supplementary angles? What are supplementary angles?
Two angles that add up to be 180 degrees.
Okay, what are linear pairs?
Linear pairs are, it's a line, and a line is always 180 degrees.
So it's two adjacent angles whose non-common sides make a line. Okay, so if two angles add up to 180, do they have to be adjacent to one another?
No. It can literally be like one opposite end of the page over here, and then another one over here.
Yep.
It's still equal 180.
So if I drew something like this, and let's say that this is 160, let's make it 140 degrees. And that's about 40 degrees. Are they supplementary?
Yeah.
Yes. Are they a linear pair? No. So this is a counterexample. Okay, any questions about that? All right.
Fun part.
Mr. Davis, quiz. Is math like fake?